Alright, well, welcome to another video. Today I'm going to share with you an algorithm for solving problems with energy. I'm going to talk about energy and then discuss this algorithm that I've written down here for solving problems using energy instead of forces or kinematics or what have you. And so we're going to talk about this algorithm, and then we're going to see how it's applied to a system. And then so we'll go through this algorithm, apply it to a real example or a real problem. And yeah, so we'll see how that works. This is M58 if you're following along at home in the blue book. Actually, there's two parts to this question, and the first part is to determine what K is, given some other conditions. But you don't need to use energy for that part, you just need to draw a free body diagram and sum some forces. So I'm just going to start assuming that we've solved for K, and so we'll think about this problem given K now. So assuming that we've already solved the first part to determine what K is, which is just free body diagrams and Newton's laws and things like that. Okay, so the situation we have here is that there is a mass. Well, this is an elevator actually, they're calling it. We have a little elevator. Never seen an elevator like that, but I don't know, maybe it's for hobbits or something. But anyway, we have an elevator and there's a spring that it's going to land on, and we're told that the elevator cable breaks and it starts falling down, and it lands on its braking support system, some safety mechanism that's modeled as a spring. And we're told that at this instant, when it just touches the spring, there's some velocity v, which is 4 meters per second acting, or 4 meters per second downward. And the question wants us to know, okay, how far is this spring going to compress given this initial condition? So that's the problem. We're going to solve this with energy using this algorithm I've written down here. So let's talk about that for a minute. So I think this is a pretty general framework for solving energy problems or solving systems like this with energy, let's say. And so the step one, I call it draw snapshots of the system at particular moments in time, and then label them. So what do I mean by drawing snapshots? Well, we consider our system at particular moments in time. For example, right when it's here, when we know things about it. So right when the elevator is about to start compressing the spring, so just as it's come into contact before the spring has had any time to compress, we know what the velocity is. So we're probably going to choose that as one of our snapshots because we know information about it. So the second snapshot we'll draw is when it's down here and the spring's fully compressed. So that's what I mean by drawing snapshots. And then the whole point of that is we'll be able to, at the end, apply conservation of energy between the two frames, which will give us an equation that we can solve for whatever parameters the question's asking for. But before we can do that, we draw pictures. We draw pictures of the system and we label them 1, 2. Maybe there's more in more difficult problems, but in this problem there's just 2 snapshots we're interested in. And then at each snapshot we're going to determine what the energy is. So maybe there'll be a kinetic term, potential term, and we'll sum them together, get our total energy at that moment. And we're going to, I have a caveat here that we should make sure to choose a common zero. And this comes into play when we're talking about gravitational potential energy. We'll talk more about that in a bit when we see it applied to this problem. 3, we'll ask ourselves, is work being done on the system? And if yes, is that work adding energy to the system? For example, a person pushing on a block would be adding energy into the system, while a frictional force might be removing energy from the system. So we ask ourselves, is there work? And if yes, is it adding energy or removing energy? And finally, we apply conservation of energy between our 2 snapshots, between our 2 frames. And maybe we need to consider work in there. That's why 3 is here. Okay, so let's see if we can apply this algorithm to our problem at hand. And pardon my erasing, I will give ourselves some more room to work with. And let's draw some snapshots. So the first snapshot, like I said, it's basically the same picture I just had, but let's call it 1. And so we have our spring here. The spring is fully extended. The elevator is tumbling down at some velocity v, which happens to be 4 meters per second. And the spring is fully extended here, or I guess it's not extended or not compressed, but it's at its just equilibrium length. And so we'll let that be our first snapshot. And our second snapshot, now since we want to know basically how far it's going to compress after this system has had time to evolve, we're going to choose our second snapshot to be at that position where it's fully compressed. So let's imagine it's compressed that much. Our elevator's down here now. And if I want, I can draw, where the equilibrium would have been, just for reference. So yeah, that's 2. And we know also here, because we're assuming, we want to know the maximum amount it compresses, so we can safely assume that at this point the velocity is going to be 0, because if the velocity wasn't 0, then it would continue to compress the spring, and therefore we wouldn't be interested in it at that point. So we can take v to be 0 here. And yeah, so that's step 1. Okay, we've drawn some pictures, and we've got an idea of what's going on with the system. So next thing to do is to determine the energy at each snapshot, with the caveat that we should make sure to choose a common 0. Okay, so well, in general, the energy at 1 and 2, but let's start with 1, is going to be a kinetic piece, which I'll call KE1, and a potential piece, PE1. Now, kinetic energy in general is given by 1/2 mv squared. The potential energy actually can have several sources, but for example, the gravitational potential energy, which I'll call PE sub g, is going to be the mass times the gravitational constant times h, where h is the height above what we've chosen as our 0 point. Now, remember that we are free to choose our 0 reference point anywhere we like. So we could choose it here to be 0. We could choose it here if we wanted to. But the point is we can choose it anywhere we like, because in physics we can only measure differences in energy. So as long as we choose a reference point and then measure potential energy in both cases relative to that point, we've taken care of the potential energy correctly. So we'll see how that plays out in a minute. But this h, I guess, in general, say if this was 0, then h would be the distance from here to here. But actually it'll turn out we're not going to choose this as 0 because there's a better choice. Another source of potential energy, PE sub k, I'll call it, is the potential energy built up in a spring. So that's given by 1/2 kx squared, where x is sort of, if you have a spring sitting here at some at equilibrium, x here is 0. But if I perturb it a bit, if I pull it one way or push it by the same amount, that difference between its equilibrium position and its current position is what goes into this formula, x. And this is indeed a potential energy because, well, think about it. If you squish a spring, there's energy now built up in that spring, ready to release and do some work. So it is truly a potential energy. Excuse me. So anyway, that was E1. We have a kinetic term and a potential term. E2, we're going to have a kinetic term in general plus a potential term in general. Now remember, if KE is 1/2 mv squared, in this particular instance, so this is again when the elevator has reached the farthest down it's going to go and the spring is compressed the farthest it will, we can take the velocity to be 0. So this term is 0 because Ke is just 1/2 mv squared, and if v is 0, Ke is 0, or the kinetic energy is 0. The potential energy here comes from two sources in general, right? We'd have a PE from gravity, 2, carry the 2 around. And then we'll have a PE from the spring. Okay, but here's where our choice of 0 is going to make our lives a lot easier. So at the beginning I was saying, oh, we could choose our 0 here, and we could, but we won't, because turns out if we choose our 0 here, then the gravitational potential energy, this term, which in general would be mg times h, well, the height of this above the 0 is actually 0. So if we choose our 0 wisely here by putting it at the farthest place down that the elevator will go, we can completely eliminate this term altogether. And so the only contribution we have is this PEK squared, which is going to be a 1/2 kx squared kind of thing. And the compressed length will be this distance here, which I'll call h. Okay? So then we can have this as 1/2 k h squared. So, I mean, this is the caveat I'm talking about, is making sure we choose a common 0. If we choose this as our 0 in this snapshot, we better choose it as 0 in the other snapshot. So it's helpful to draw the diagrams right beside each other so we can, extend lines through. That means that this is 0 too. Okay? And in fact, given that the spring was uncompressed here, this line up is the same as this line. And so in fact, this is h as well. And so now, our kinetic energy is 1/2 mv squared, right? From this definition. And our gravitational potential energy is the mass times gravity times, well, h, right? So again, in choosing our 0 here, we've eliminated one potential term from the system and we've made our lives easier. Okay, so this is the second step of the algorithm. So to reiterate, 1, we've drawn our snapshots, and 2, we've determined the energy at each particular snapshot. And we've made sure we've chosen a common 0 in both reference frames, or in both snapshots. Step 3 is to ask ourselves, was any work being done in the system? And the answer is no. You could argue, and you would be right, that there was gravitational work being done from this case to this case, but we've included that already in our potential energy term here. And I prefer to do it this way instead of treating gravity as work, just because, I don't know, that's how my mind works, so maybe you don't prefer to, but anyway, I digress. We have no other work going on, so we can go right to step 4 and apply a conservation of energy, which is just to say that the energy at snapshot 1 is equal to the energy at snapshot 2. This does not hold if there was work, but I'll explain an example where we have work in just a moment. So now all we have to do is sub in our equations here. Okay, that's the left-hand side, and this is going to equal 1/2 k h squared. And as it turns out, h is actually what we're interested in solving, right? Because h is the amount by which the spring is compressed after the elevator falls on it. And what we have here is actually a quadratic equation in h, right? And we can solve this equation because we know k. They gave it to us in the problem. If you forget, just look in the description of this video. We know what m is, they gave us that, and so this is just a quadratic in h, right? Because we know what v is also, it's 4 meters per second. And you can solve this and you'll find that h is 1.3. Okay? So that's how we've gone through the algorithm for a simple example. I'd like to back up a minute and go back to step 3 and imagine that we had some work going on, some work present in the system. So the way I'm going to introduce work is, imagine that there is a wall here. And I guess there's one here too. So there's a wall here and it has some coefficient of friction mu. And so as this elevator falls, it is sliding against the wall, and so there's going to be some frictional force, right, acting on it that way, up the wall as it tries to slide down. So in general, the definition for work is the force times the displacement, okay? Or actually times the distance, not displacement. It's an important distinction. In this particular example, they happen to be the same, but we do indeed mean distance and not displacement. So this distance corresponds to the distance over which the force is acting. So in this particular example, the elevator starts here and it slides down this far, or it falls down this far. So it is actually this distance h over which the force is acting, right? Because it starts here, comes down to here, it's moved a distance h. And so in this particular example, our work of friction would be force of friction times h. And I don't mean a dot product, it's just a bad habit I have of drawing my multiplications as dots. Now, it's just come to my attention that this distinction between distance and displacement here, because if we imagined instead that this elevator was vibrating up and down, right? So it's just sliding up the wall, down the wall, up the wall, down the wall. If we were just considering the displacement, all we would have is the friction that acts from this first sort of movement up and down. But in fact, if it's oscillating like this, then the friction's acting the whole time it's moving. So, it's several distances that it's covered, several displacements that it's covered if that was actually happening. So we have to be careful we mean the total distance here, right? Because if it was oscillating like this, we'd have to add this part plus this part plus this part plus this part plus this part and so on. But anyway, here we just have one sort of cycle, one oscillation. It's just moving down, so we can safely put h. And as I was saying, we have to ask ourselves, is it adding or removing energy from the system? And here it's removing energy. As I mentioned at the beginning, friction saps energy from the system. So we would say this is removing. And how this is going to manifest itself is in our conservation of energy equation. So now, instead of this, E1 equals E2, what we actually have, well, I'll write out E1, leaving a space here because I know I'm going to put something else here. It would be equal to E2 if there was no work being done on the system. However, we do have some work being involved, some work being done on the system. And if we think about it like this, the energy here is E1, and the energy here is E2. And if some work is being done on the system as the system transitions from 1 to 2, then the energy at 2 is going to be less than the energy at 1, because as 1 has transitioned to 2, it has lost some energy due to friction. So we write E1 minus the work done by friction is equal to E2. And this makes sense, right? Because, again, if the E1 is sort of the energy of the system at the very beginning, and E2 is the energy of the system later on, well, E2 would be equal to E1, except that some of that energy has been lost due to friction. So we have to subtract that work done from the initial energy to get what the energy is at E2. And then we just, would go about solving this problem in the same way. I don't think you have enough information here to actually solve this, because we need to know what FF is in terms of mu and n, where n is the normal force and mu is the coefficient. But actually, the way I've drawn it, there is no normal force, so we'd actually probably need another force applied this way to get a normal force. But anyway, it doesn't really matter. If there is a work being done and they give you enough information, this is how you apply your conservation of energy equation, instead of just jumping to E1 is equal to E2, okay? And then the last thing I want to say is to go back to this choice of 0. I was dwelling on it a little bit, but I want to show you why it's only differences in energy that matter. So let's go back and say we had chosen this as our 0 point. Okay. Then the height of the elevator at this instant would be this height, okay? Call it h1. And then if this was 0, then I would call this height, let's say h2, okay? And then our equations would read, our E1 would be, well, the kinetic term still, that doesn't change. But now we have an mg h1. That's fine. All that's happened is we've gone from our 0 here and a height here to our 0 here and a height of h1. So that's not too surprising. But now E2, that's an interesting way to draw E2. E2, right, is going to be, now we set it to 0 in the original case because we chose our origin at the height of the elevator at this point in time. But now our origin is down here, so the height is whatever this distance h2 is. So now we're going to have an mg h2, and also our expression for, well, actually it will be the same. I was going to say it changes, but it actually is the same, right? Because if we look at the way I've drawn it, if this is h1 and this is h2, then h is just h1 minus h2. So that stays the same. But now notice the difference here is that we have this potential term that's shown up in our energy at the second snapshot. And so if we were to, again, assuming that work is 0, the work is 0, right? We can go right to saying E1 is equal to E2 as before. But now if we do that, unfortunately I'm running out of room. If I write E1 is equal to E2, what I'll have is 1/2 mv squared plus mg h1 equal to mg h2 plus 1/2 kh squared. And if I rearrange this to bring this term to the other side, I'll have an mg h1 minus mg h2 plus this kinetic piece. And importantly, you notice if we zoom in on what we have here, what this is the difference in energy. It's the difference in potential energy between here, here and here, which at the very beginning is what I was saying is that we can only measure differences in energy. We can't measure absolute values of energy because it's, in this context, it's meaningless. So this is a difference, and that's exactly what we were measuring here. But we just saved ourselves some work by choosing the origin at 0, the origin where the height is 0, to be at where it was in the second snapshot. Now I could go even further and say mg factor out h1 minus h2, assuming this stuff stays the same. But again, h1 minus h2, h1 minus h2 is just h. So it does indeed reduce to our old equation. But we saved ourselves a little bit of work, I guess not that much, but a little bit of work by choosing our origin wisely. So I hope that helped, and I hope you can apply this algorithm to more difficult problems. But yeah, thanks.